Swayam Prabha. Digital India. Educated India.
So now let us make material balance over time del T. So now we have W dot, which is moles per second at what rate naphthalene evaporates over del T, and this we equate with rate of change in the mass. So the volume is 4 by 3 pi RQ. So this would be the volume multiplied by the density divided by the molecular weight. So essentially we are saying that over this del T time, this naphthalene ball evaporates and the size decreases by del R. So we have del R, and over this time the mass decreases, or the radius decreases from R to R minus del R. Okay, so which means if we take a limit of del T tends to 0, we can write del W dot as d by dt of 4 by 3 pi RQ cube rho over m, which can be written as 4 by 3 pi R square rho over m dr by dt. So we have rate of change of radius of this naphthalene ball equated with respect to rate of change of this W dot at what rate the naphthalene diffuses over the length R to infinity. Okay, and already we have obtained this expression for W dot diffusion flux moles per second or kg per second in our previous lecture, previous slide here. So if we just substitute W dot, we have ln P over P minus P naught 4 pi P is the total pressure, DAB binary diffusion coefficient of naphthalene in air over RT equals 4 by 3 pi R square rho over m dr by dt. So we can simplify R with this 4 pi will get cancelled with this, and now we can integrate. So entire expressions, which is actually W dot, we are assuming that it remains constant over the integral. So dr by dt, if we integrate from R1 to R2, we will have total time for a decrease in the radius from R1 to R2 as T ln P over P minus P0 P dAB m over RT rho equals R1 square minus R2 square by 2. So this is on the integrations. Now all we have to do is substitute the correct values of R1 and R2 and find out the total time, which is the question asked here. So the volume V is 4 by 3 pi R1 cube T equal to 0. So R1 is 3 V over 4 pi 1 over 3, and the volume we can write in terms of 4 by rho into 1 over 4 pi. So rho is the density here, and if you recall this T equal to 0, to start with the weight is 4 kg of the naphthalene sphere. So we have R1 here, which if we substitute, we should get 9.426 10 to power minus 3 meter. Similarly at R2, when the mass becomes 3 kg here, if it's just a normal substitutions, we can get R2 as 5.94 10 to power minus 3 meter. and then that if we substitute in our expression which we have obtained on integrations, we have T ln P is the total pressure 1.013 over 1.013 minus the vapor pressure or the sublimation pressure is 0.8054 over 760 equals 1.013 10 to the power 5 total pressure. Diffusion coefficient is given 6.92 10 to the power minus 6. Molecular weight is 128. R is 8314. Temperature 318 Kelvin. Density is 1140. This equals R1 square minus R2 square, and R1 is 9.42. 6 10 to the power minus 3 square minus 5.94 10 to the power minus 3 square over 2, and then if we calculate, T will equal approximately 8000 seconds, which is nothing but 222 hours. So it takes a long time for the mass of naphthalene ball to get down from 4 kg to 3 kg. So the example which we have chosen here is nothing but diffusion in spherical coordinates, and you should be able to compare this example to the previous example which we had, where we had this Cartesian coordinate system. So two examples are similar. One is in Cartesian coordinate and one is in spherical coordinates. The difference is that under steady state, in case of coordinates, Cartesian coordinates, kg per second or kg per second per meter square of diffusion plane remain constant. In case of spherical coordinates, it's only the kg per second which is conserved. Kg per second per meter square or moles per second per meter square, it changes with the radius. So these are the three different examples we have taken for very basic examples to calculate diffusion flux Na over a diffusion length del z given operating conditions like pressure, temperature, and the concentration gradient. All right. Now what we do next, we take up a new topic, mass transfer coefficients. You may be familiar with this, mass transfer coefficients. Now before we get into this, we must ask this question, what is this coefficient? Is it a fundamental variable? Is it a physical variable defined here, or it's something engineering parameters? The answer is that mass transfer coefficient is not a fundamental variable, fundamental quantity. It's an engineering parameters. It has been introduced or it has been defined to make our computations simpler. Now if you can go back to all those three examples, we said that we had one example where we had counter diffusion, or where we had a stagnant medium B, etc. We could calculate how much is the diffusion flux over this diffusion length Z. The problem comes when the flow becomes complex. So it's a hydrodynamics. We said in the beginning class, you should have some knowledge of hydrodynamics. So it's the hydrodynamics, the fluid flow, and if the fluid flow is complex, it may be difficult, quite difficult to solve for the velocity profile and then predict this diffusion flux. In those cases, mass transfer coefficients become an engineering parameters, which is we have to estimate from some given operating conditions. Then we can apply this to calculate this diffusion flux. So let's take few examples where we are trying to say that we should make use of mass transfer coefficients, or we may not be able to make use of the general expression which we obtain for diffusion flux in terms of diffusion length, etc. So for example, so the question we are trying to answer here is that why there is a necessity for defining this mass transfer coefficients, or what is this motivation. So if you recall, if we have a tube and if the Reynolds number is less than 2100, we have well defined velocity profile which is parabolic. P equal to, we can write 2 V bar is average velocity 1 minus r square over r square. So this would be the radius of Now if you have the velocity profile like this in a tubular, and if you are asked to calculate diffusion flux Na, it should not be a difficult thing, in the sense that we can substitute this velocity profile in our Navier-Stokes equations. One can solve for the concentration profile, and then we can calculate diffusion flux, etc. We know the bulk transport, it would be V into Ca. So once we know the diffusion flux, once we know the bulk transport, one can predict the diffusion flux. So the problem is not here. This is a straightforward case where we have a tubular flow and we have well defined velocity profile. Things could be more complicated if the Reynolds number goes very high, say turbulent. If you have turbulent, then recall from your hydrodynamics, you will have a tubular flow and the velocity profile will start becoming, or will become flattened. So here we have velocity profile where in the core the velocity is almost nearly constant at some v velocity or v bar, but near the wall we have a gradient, a velocity gradient. Now as it is in the case of turbulence or turbulent flow, when the Reynolds number is much larger or larger than 2100, there is unpredictions, there is a uncertainty in predicting this velocity here. As a consequence, we cannot apply exactly the Navier-Stokes equations and we can solve for this diffusion flux. In those cases, we will like to say that yes, if we know the concentration gradient or we know the concentration difference from C wall to say C bulk, one should be able to write that diffusion flux equals some constant K into this concentration difference. So this is what we are trying to say here, that this K is nothing but mass transfer coefficients. In principle, if hydrodynamics is well defined, if you have the velocity profile like in laminar flow or viscous flow, there is no necessity for mass transfer coefficients or defining this mass transfer coefficient. It's very important that we understand the motivation here. Mass transfer coefficient is an engineering parameter. It's an engineering parameter. It's not a fundamental variable. And this type of parameter is required when we have uncertainty in hydrodynamics, in the prediction of velocity profiles. There this mass transfer coefficients become quite handy. We'll take, for example, once again, suppose we have a sphere and this naphthalene ball, it evaporates similar to the previous case where we have this velocity profile like this. Okay, so the fluid approaches from infinity to this V infinity. We have this radius of this ball which is r, and we have been asked the same questions, what is the diffusion flux here in r. Now if the velocity profile is known to us, Pr, okay, one can predict this diffusion flux in A over a length say between r, r1 or between r2. If the velocity profile is well known defined, one can calculate this Na starting from Navier-Stokes equation in spherical coordinate, etc. The problem comes when we have very high Reynolds number, very large, say 100 Reynolds number based on the particle size. If it's very large, say 100, then there is uncertainty in the velocity profile. And if you recall from your aerodynamics, we will have cases of boundary layer separation, etc., or the ADs which is formed at the this rear end, in which case it's to predict diffusion flux in terms of your bulk transport VCA and diffusion flux, it becomes it involves a lot of error here. In these cases, it's possible to define a mass transfer coefficient quantity and to say that we have the flux now, which we can write as diffusion flux Na as mass transfer coefficient into some concentration difference, where del C is concentrations difference between Cs at the surface and this C infinity. Okay, so we are trying to make a case here. What is the motivation of mass transfer coefficients? Why we have to define this quantity, and where we can get away without defining this mass transfer coefficients. We saw two examples where we have very straightforward case where we have a tube and certain pool of the liquid it evaporates, or we have an naphthalene ball which evaporates. In those cases, we said that let's assume that NB is 0, the bulk transport is 0, and then we can calculate this diffusion flux. So if suppose we have a packed bed, certain more complex situations here, like we have packed bed in which different spherical particles are stacked like this, and the fluid goes like this. So if you look at one sphere or one spherical particles, there is a quite complex velocity profile surrounded around this. To predict velocity profile exactly, one requires things like software engineering tool like CFD, computational fluid dynamics. Then maybe to some extent we can predict the exact nature of this velocity profile. Otherwise, it's very difficult to predict the fluid flow inside the packed bed. In such cases, again, the concept of mass transfer coefficients is quite important here. So we would like to go back to again the general expression which we obtained for diffusion flux, and see how the same expression can also be rearranged or can also be modified to introduce this engineering parameters Km mass transfer coefficients. Okay, so let's revisit this expressions for we assume a steady state, no chemical reactions. So we have Na equals Na over Na plus Nb. We wrote DAB C over Z ln Na over Na plus Nb minus XA2. We can write in terms of mole fractions at the plane 2 over Na plus Nb minus XA1. So this Z is nothing but diffusion flux, diffusion length, and XA1 and XA2 is your mole fractions across the plane 1 and 2. Okay. Now if we take again the simpler case of case 1, where we say that B is stagnant B, we can write Nb equal to 0. With Nb equal to 0, Na over Na plus B is 1, and then Na equals, or simplified to, DAB C Z ln 1 minus XA2 over 1 minus XA1. We can also write like DAB C Z, we can divide and multiply by XA1 minus XA2 over XA1 minus XA2 ln 1 minus XA2 over 1 minus XA1. So all we are trying to do the similar expressions we have rearranged and written like this, and then further we can write DAB C over Z del X. So now we are introducing this mole fraction difference between plane 1 and 2, which is nothing but XA1 and XA2. And here what we have ln XB2, mole fraction of B at plane 2, 1 minus XA2, and B is stagnant here, XA1, and XA1 minus XA2 can also be written, sorry, this should be XB1. So we have XB1, and then XA1 minus XA2 can also be written as XB2 minus XB1. Just subtract 1 minus this, which means now we have an expressions for mole flux in terms of DAB C Z into ln. If you recall, if you try to recognize this term here, we have XB2 minus XB1, a quantity like this, we call it XBM. It's a logarithmic average, which is nothing but XB1 minus XB2 over ln XB1 over XB2. So just like we have an arithmetic average or geometrical average or harmonic average, we have been able to obtain an expressions for diffusion flux of A when B is stagnant in terms of known quantities here, and concentration difference, we have x bm here. Okay. Now here comes the concept of this mass transfer coefficients. The entire quantity on the left in the parenthesis, we can call it as kx into del x. So what we have obtained here, we are trying to say that diffusion flux, it's a proportional to del x, and the proportional constant which we got as kx, or we are writing as kx, we are calling it as a mass transfer coefficient. So again, let's go back what we said in the beginning. What is the motivation of introducing this mass transfer coefficients? What was the objective? We said that in those cases where the hydrodynamics are complex, it's difficult to solve the velocity profile, or there is uncertainty in solving the velocity profile or fluid flow, just like a flow in a packed bed, very complex situation there. Or we have high Reynolds number when we have a turbulent flow, not viscous, not laminar, then there is a uncertainty in predicting the velocity profile. In those cases, it's not possible to solve analytically an expression for diffusion flux, which we have obtained so far. We took two examples of case 1 and case 2. So all we are trying to say here, that we are trying to introduce the concept of mass transfer coefficient is the way it is defined. Diffusion flux in A equals to a quantity kx, which we are calling at a mass transfer coefficient, into del x. Del x is nothing but your concentration difference, is your mole fraction across the plane 1 and 2. We can also write Na equals kx, some different prime, we can give into del c, where c is now the concentration difference is Ca1 minus Ca2. All right. So there are different ways of writing this diffusion flux. In case of the case 1, when the other medium, other component B was stationary, we can write Na like kx, or some proportional to concentration difference or mole fractions. Let's take case 2, when we said that we have equimolar diffusions, and let's see if we can write similar expression, or we can develop similar expressions for diffusion flux. So case 2 we studied in the last class, earlier classes. We had Na equals minus Nb, which is equimolar counter diffusion. Okay. So when we have Na equals Nb, then Na equals, we can go back to the same expressions which we started earlier. We can substitute Na equal to minus Nb to write N dAb Z C XA1 minus XA2, which is even simpler than the previous case. And again, we have the same situations. We are obtaining expressions for Na. We are saying that is proportional to mole fractions across the plane 1 and 2. And here the proportional constant K equals dAb C over Z. So two cases which we studied here, very simple, very fundamental. They form the basis for all our calculations, or all the examples which we had in the previous classes. Now we are trying to say that we have same expressions, we have arranged in a different way, and we are getting the similar expressions, that diffusion flux is proportional to concentration across plane 1 and 2, or mole fractions across 1 and 2. Or if you have gas instead of liquid, we can say that diffusion flux is proportional to difference between the partial pressure at plane 1 and plane 2. In these cases, of course, there is no necessity, the example which we took, to define mass transfer coefficients. But as we said earlier, that if we have very complex hydrodynamic situations where the velocity profile cannot be solved with accuracies, mass transfer coefficient becomes an engineering tool. We can define Na diffusion flux equals a quantity Km mass transfer coefficient multiplied by concentration difference, the potential difference between the mole fraction, difference between the concentration, difference between the partial pressure, and 1 and 2. And all complexities of hydrodynamics will be now embedded in mass transfer coefficients. So that means we can conclude that flux moles per second per meter square can be written as Km into del C, or can be written as del X or it can be written as K into del P. Of course, the values of Km will be different in all cases. Generally, we write Kx, we write Kg if it's a gas here, and instead of, if we're using concentrations, we can write as Kc. All of this is a mass transfer coefficients. Km, mass transfer coefficients. So all it means, if we have gas system, we can also write Na as Ky into Y1 minus Y2, where Y1, Y2 are the mole fractions, or we can write as Kg P1 minus P2, where P1 and P2, these are the partial pressure of one at the plane 1 and 2. And let's write down here that in principle, we do not require K or mass transfer coefficient Km in laminar flow. Why? Because laminar flow is well defined. It's a flow we have seen in case of tube. We have analytical Navier-Stokes solutions, V equal to V max 1 minus R square over R square. So in those cases where the velocity profiles are well known, there is no need to define Km to calculate molar diffusion flux. But we do not require Km in laminar flow because molecular diffusion prevails in such flow. In fact, you should like to recall the hydrodynamics, the concept of friction factor and drag coefficients. If you are asked to calculate pressure drop in a tube, you can use Fanning equations, which contains friction factor. You can also use Hagen-Poiseuille's equations if the Reynolds number is less than 2100. Okay, but if the Reynolds number is larger, much larger than 2100, then we use friction factor or Fanning equations, which contains friction factor. Then we rely on experimental data or Moody's plot, which is obtained from some experimental data to predict this, to calculate or estimate this friction factor. So the idea is that use of Fanning equations, we can use Fanning equation very well in case of laminar as well as in case of turbulent. In case of laminar flow, if we use friction factor is 16 over Reynolds number, which can be obtained if we equate this Fanning equation with the Hagen-Poiseuille's equations. How did we get Hagen-Poiseuille equations? We had the velocity profile. We said that the pressure drop equate with the shear stress multiplied by the surface area, etc. One can calculate an expression for pressure drop. Then you define friction factor in terms of pressure drop and the kinetic energy per unit volume, etc. to show that friction factor equals 16 by Reynolds number. But if the flow is turbulent, then we have to rely on certain experimental data, because in turbulent there is uncertainty in predicting velocity profile. Similarly, CD, drag coefficients, we said CD equals 24 by Reynolds number if Reynolds number is less than 1 or if we have a viscous flow. But how do we get CD equal to 24 by Reynolds number? We start from the velocity profile. We take a spherical geometry, solve Navier-Stokes equation in the spherical coordinates. We obtain the velocity profile. We solve for the gradient. Then we calculate shear stress. And then we obtain the force 6 pi mu v r, which we call it a Stokes law. If we take this force and define drag coefficients, then one can show that CD equal to 24 by Reynolds number is nothing but a calculated. It's an analytical expression for drag coefficients. What happens if the Reynolds number is very large? In that case, CD one has to rely on certain plots or experimental data. So the motivation of defining mass transfer coefficient here is also the same. If the flow is well described, like in laminar flow, in viscous flow, there is no need to define mass transfer coefficient. We can use the expressions for Na in terms of diffusion length Z, and we can do the calculations. But if there is a complexities like in a packed bed, tower, or turbulent flow in a tube otherwise, or the flow past a simple sphere but at high Reynolds number. So wherever there is a complex situations, velocity profile is not accurately known, mass transfer coefficient quantity is defined to predict this diffusion flux in terms of mass transfer coefficient and concentration difference by the partial pressure across the diffusion planes. How do we get mass transfer coefficients? One has to rely extensively on experimental data, and in those cases we will see that we define a quantity like Sherwood number, which is Km L over diffusion coefficients. This L is characteristics length, which means different geometry, different situations, L will be different. D is diffusion coefficients, which is meters square per second. L is meter, and Km is meter per second, mass transfer coefficients. If we define as N A moles per second per meter square equals Km into del C, concentration difference moles per cubic meter. Okay, so in literature you will see that there are several cases which people have studied, and there they have estimated mass transfer coefficient in terms of certain dimensionless groups like Reynolds number, Smith number, from which we obtain this mass transfer coefficient Km, and then we can predict diffusion coefficients. So you are required to visit a table in Trebol, which is table 3.1. You will see that table given in Trebol 3.3, I beg your pardon, where we have several such cases, 1, 2 listed. We will just note down a few of them. One is very common. If you have flow past a sphere, so if you have a flow past a sphere, or you have flow in a tube, okay, or flow in a packed column. So there are several such examples given in this table where Sherwood number, in all these cases, Sherwood number has been given in terms of, mostly in terms of Reynolds number and Smith number. So SC is Smith number. Which is nu over d. So kinematic viscosity nu meter square per second, and we have this binary mass transfer coefficients meter square per second, dimensionless numbers. So you are required to visit this table 3.3 and see how we can define this mass transfer coefficients. The idea is that all these correlations which have been developed in terms of Reynolds number and Smith number, they are extensively dependent on experimental data. So when you take up a problem or an example, you must do a literature survey. You must go to visit such table like 3.3, Trebol or Perry's Chemical Engineering Handbook to use an appropriate correlations, from which you can calculate this mass transfer coefficients. Then you can predict this diffusion flux. We just for an example, suppose we have what is given. You have a single sphere, and we have a flow like this, right? So it's a similar example that we have a sugar ball or salt or naphthalene ball, and we have been asked to predict this mass diffusion flux NR. Okay, so if we have some fluid flow here, there is a Reynolds number based on the particle size, which we can define as V infinity. Flow velocity at a very far stream is V infinity. dP, diameter of the particle. Rho of the fluid, and mu f, rho f and mu f, these are the physical properties of the fluid. We can define Reynolds number. Similarly, we have Smith number, nu f over DAB, binary diffusion coefficients of A in B. So in these cases, correlation is given as Sherwood number equals 2 plus 0.347, Reynolds number, Smith number to the 0.5, 0.62. More important to note here is that the author has given the range of Reynolds number into Smith number to the power 0.5, this quantity. This expression holds good if the value is between 1.8 to 600,000 and Smith number between 0.6 to 3200. Now this is an empirical correlations. Empirical correlations. All it means, this has been obtained based on certain experimental conditions where we meet these two restrictions. And then once we know Sherwood number, we can calculate Km. Once we have Km, we can predict diffusion flux Na as Km into del C. The idea here is that Reynolds number and a Smith number, certain conditions, it's not possible to define this velocity profile or to calculate the velocity profile and to obtain the expressions for Na. If fluid is stagnant, you can make out that this term will drop, and then we have Sherwood number equal to 2. Now Sherwood number equal to 2, when the fluid is stagnant, one can obtain analytically. As an exercise, you can try Sherwood number to obtain Sherwood number equal to 2 if the fluid is stagnant. So we are trying to give the same message again and again, that definition for mass transfer coefficient is purely arbitrary. It's an engineering parameter. It's not a fundamental variable. It has been defined to make our calculation simpler in those cases where there is a complexities of defining or solving this velocity profile. So similarly, we can take one more example, like we have flow inside a circular pipe. So if the flow is inside this pipe, if the Reynolds number is very large, or say Reynolds number is 4000 and greater, then the velocity profile will not be parabolic and we have some flat velocity profile. In this case, if we are asked to calculate diffusion flux from the wall, let's say we have certain species which diffuses from the wall or to the wall. In this case, Na can also be written as mass transfer coefficient into concentration difference, which means we can write Km as C wall minus C infinity. So we have Cw wall and we have very far from the wall C infinity. So this is the advantage of defining this mass transfer coefficients. Complexities of the velocity profile Reynolds number is embedded now in mass transfer coefficients. And how do we get Km? So there is a correlations given in terms of, again, Sherwood number, which would be 0.0023, Reynolds number to the power 0.8, Smith number to the power 1/3, and then the author has given a range that this equation is valid between 4000 and 60,000. Look at the range here, it's a turbulent flow. It's not like the previous case or the simpler case when we have the flow is laminar and we have the velocity, parabolic velocity profile, like V equals 2V bar 1 minus R square over R square. So in case of turbulent flow, where there is uncertainty in predicting this velocity profile, we can come out with this correlation. The author has come out with this correlation based on the experimental data with the range, with the restriction that Reynolds number is between 4000 and 60,000 and Smith number is between 0.6 to 3000. So once again we have given this example that where there is a necessity of defining this mass transfer coefficients. Similarly, we can take one more example, which is more engineering flow in a packed bed. So if you recall, in the first two lectures we talked of this packed columns. We have the absorption column and we have sulfur dioxide rich air and we want to remove by absorptions. So generally in these cases you have a column packed with certain packings to improve contact between the gas and the liquid. So if you have the packing like this, where we have certain packings stacked, it could be spherical, could be cylindrical, etc. It's quite a complex velocity profile. The liquid goes like this and gas flows through this, across this or between the pores, micro pores of cylinders and this air, this gap here, the flow is quite complex. in which case again the necessity of mass transfer coefficient becomes indispensable. And in this case also we can write mass diffusion flux in A as Km into del C, concentration difference between the surface and the bulk C infinity away from this packing, etc. So in this case also Sherwood number, now in this case diffusion flux, or sorry, I beg your pardon, mass transfer coefficient is estimated from a factor called JD, which is related to 2.06 over epsilon Reynolds number minus 5.75 equal to friction factor by 2, but this JD is also equals Sherwood number over Reynolds number into Smith number 1 over 3. So again we have the similar story here. To calculate mass transfer coefficients we required Sherwood number, which is Km characteristics length over diffusivity. In this case L would be equal to the diameter of this particle of the packing, etc., or equivalent diameter of this packing. So from here we can calculate the mass transfer coefficients and can predict the diffusion flux. In this case also there is a restriction that Reynolds number must be between 90 to 4000. So in this Reynolds number is again defined with respect to the diameter of the particles, and whether if the Reynolds number is 90 to 4000, all it means much larger than 1, and we have a turbulent flow here. So the velocity profile is quite complex, and hence there is a necessity for defining mass transfer coefficient. Smith number is given as 0.6. So essentially again we have taken 3 examples to show that mass transfer coefficient is an engineering parameter. It has to be estimated, it has to be correlated from the correlations available in the literature. If the situation which you are trying to model or which you want to study, for that situation if the mass transfer coefficient is not given, then one has to obtain experimentally. Okay, in those situations where the Reynolds number is very small, flow is well defined, viscous, laminar, one can invoke this Navier-Stokes equation, calculate velocity profile or the velocity, superimpose on a species balance, and can solve for the concentration gradients. Once we know the concentration, we can solve for diffusion flux. Okay, so what we do here now, we take up 3 well-known theories. Okay, so we are writing here that all this Sherwood number in general can be written as a function of Reynolds number and Smith number in general. Of course there could be more complexities here, but the question is that in all these cases A and B, these numbers have to be determined experimentally. There has to be some experiment behind this to calculate this different coefficients here. Now there are 3 well-known theories like film theory, surface renewal theory, and boundary layer theories. These 3 theories are quite popular, to which tells us that yes, mass transfer coefficient in some cases will be proportional to diffusion coefficient. In some cases this will be proportional to a square root of diffusion coefficient, etc. So these theories are also widely used to predict or to obtain such correlations between Sherwood number, Reynolds number, and Smith number. So we will take up these theories one by one. We will not get into mathematical details, but just to get an idea that how does the Sherwood number is dependent on this diffusion coefficients. So there are 3 theories. There are several theories. The 3 which are very common. One is film theory. The second is surface renewal theory or penetration theory. We will see there is some difference between surface renewal theory and penetration theories. And third is boundary layer theory. You may have done to some extent boundary layer theory in your previous class, etc., on fluid mechanics or hydrodynamics. We will just go through very briefly through these theories to see that how does mass transfer coefficients depends on, how does Km depends on diffusion coefficients. Okay. So the first very popular theory is film theory, and this film theory is applicable in general if we assume that we have a steady state concentration profile, and we have stagnant film. So essentially what this theory says that we have, say, two streams. Suppose we have gas here and we have a liquid across this. We assume that the film here, the concentration profile in this liquid phase is linear. That's one. This steady state profile does not change with time. So we have, say, Cg here, and we have concentration gradient just at the interface. Maybe we can use Ci. So we have Ci here, and we have this C bulk or concentration at a very far distance. We have this diffusion length del Z. So the fluid is stagnant, the film is stagnant here, and we have a steady state concentration profile. In this case, one can show that this the film theory predicts that mass transfer coefficient is approximately equal to dAB over del. Now again, we are not going into details, but film theory suggests that mass transfer coefficient is proportional to diffusion coefficients and 1 over del. So which means larger the thickness, film thickness, smaller is the mass transfer coefficients. Similarly, we have penetration theory. This was originally proposed by Higby, and this penetration theory, it says that steady state profile is not possible. Profile is not possible. So this is in contrary to what we have in case of diffusion flux. So let's see what try to understand what does the penetration theory says, which is different from the film theory. Here also we have, suppose we have this gas here and we have the liquid here. So as what we have in case of penetration theories, there is something called ADs. So if you recall from your hydrodynamics, at high Reynolds number we have this hypothetical pockets of liquid which moves from the bulk to the surface. This AD stays here for some time, in which this gas molecule that diffuses within this liquid. So there is certain contact time of this ADs at the surface. So this is your liquid gas surface at which there is a contact time of theta when the ADs stays before it gets back to the bulk. So in other words, is a very short contact between the two phases when we have a mass transfer from the gas to the liquid, in which case it's not possible for this steady state profile to establish or profile to reach a steady state. In that case, penetration theory becomes quite popular and more realistic. It has been shown that in such cases, unsteady state species balance can be written del C over del theta. So if A is the component which is diffusing from gas to liquid phase, equals dAB del square Ca over del Z square. So Z should be this direction. One can start from here. So t equal to 0, maybe the concentration here was Ca0, and at certain time this interface is exposed to Cai. Then we can write this expression and can solve to obtain concentration profile of Ca in the liquid. And once we have concentration profile in the liquid, we can calculate the concentration gradient, and one can calculate this diffusion flux. In this case, it has been shown that diffusion flux Na will also be equal to Kl Cai minus Ca0. This is what we will expect. It's proportional to mass transfer coefficients and concentration difference between the interface and the bulk concentrations. Except this Kl now equals to square root of dAB over pi theta. So this is the difference between the film theory. here now KL is proportional to the square root of DAB. Unlike the film theory, which predicts mass transfer coefficient is linearly proportional to diffusion coefficients. So we had film theory where we assume that the profile is a steady state, film is a stagnant, okay, and its linear concentration gradient is linear between the two planes, unlike in case of penetration theory, which says that there is a very short contact between the gas and liquid. In other words, there is no time for the concentration profile to reach a steady state. In that case, we write an unsteady state balance. One can solve for concentration gradient and can calculate the diffusion flux to show that mass transfer coefficient is a square root proportional to square root of diffusion coefficients. Similarly, we have one more theory, which is the boundary layer theories you may have done in case of aerodynamics. So we would like to conclude with the third theory, which is also popular, boundary layer theory. Now in this case also we have what we have, there's a flat plate and it's approached by velocity fluid with U0 and Ca0 concentrations. If the surface concentration is Cai, you can think of certain solutes which dissolve in this liquid or this fluid. Then there is a boundary layer developed like this, del M. We can have, similar to this momentum boundary layer, there is a concentration boundary layer, del C. And if we are asked to calculate the diffusion flux NA, we can also write here NA equals mass transfer coefficients into Cai minus Ca0. And in this case, it has been shown this one can also calculate this mass transfer coefficients in terms of Sherwood number, etc., which is Km into the length of the plate L over diffusion coefficients DAB. Okay, so these are the three theories which are quite popular to estimate mass transfer coefficients. Of course, we have to rely on extensive experimental data to predict this mass transfer coefficient.